Hi everyone, welcome to our pre-lab lecture. This is a dry lab on monitoring the kinetics of bleaching reaction using a smartphone. I know the handout talks about having different reagents such as OxyClean, distilled water, and having the color detector app from App Store or Google Play. I did perform the experiment, collected the data, and your job is to proceed with the calculation. You will need the a calculator, of course, and a scratch paper. I've collected the data. I'll walk you through the calculation on how to manipulate the data based on the information given. I'm going to share my screen here. I will be toggling between the whiteboard. All right, there is the whiteboard, there is the handout, and then there is the data sheet. There is the handout, there is the data sheet, and this whiteboard. This is where I'll be writing the equation. Nevertheless, I'll recommend that you download, all right, download the handout. You'll be referring to specific steps in the procedure in order to get the information you need to do a particular calculation. So to start off with, there are prerequisite skills you need to be well-rounded, to be familiar. Some of them you already know, all right? Some of them you already know, and I want just to highlight those prerequisite skills you will need. One is the molarity, all right? You should be able to determine the number of moles given the mass of a reagent, mass over molar mass given the number of moles, of course, molarity, number of moles over volume in liters of a solution. And then the dilution law, the third prerequisite skill is the dilution law, which is M1, V1, M2, V2. You do not need to change the volume to liters in dilution law. You can keep it in ml. And then the of course you'll also be required to use the carving skills. You'll be plotting the curves in order to determine the reaction orders. So don't worry about what is stated here on the handout. If you are to do this at home, you are going to get the thermometer to pick and stuff like this. This was when you needed the biological or Carolina biological kit, which you do not have. Nevertheless, how this lab was to work is if you had a smartphone, all right, the color detector phone, you will react the peroxide in OxyClean to see the rate at which it is decolorizing the colored food with red, blue, yellow, and green color. The objective of this lab is to, all right, the objective of this lab is to determine the rate law, which we looked at in the previous experiment, and using the method of initial rates, which we looked at last time, and the new method, which we call the graphical method of determining the reaction orders. I know probably you have covered in the lecture, but I want just to highlight how this graphical method is used to determine the order of a reaction, okay? Remember, orders are the exponent by which the concentration of reagent are raised to. This is the rate law. You look at the concentration of A raised to M, we say value have here is reaction order with respect to A, reaction order with respect to B. We used method of initial rate last time. However, you can also use the graph. Let me show you the three most common plots you will come across and how you will use to determine the order of reaction. Let's look at the zero order. Forget about the integrated rate, low half-life, and stuff like that. But look at the plots, the graphs down here, which you will generate from the data I have on the data sheet. If you plot the concentration on y-axis versus time, and you get a negative slope, then you make a conclusion that the reaction is zero order. If you plot the natural log of concentration of a reagent versus time and you get a negative slope, then your conclusion is it is first order with respect to that reagent. If you plot the inverse or reciprocal of the concentration versus time, you get a positive slope. You make a conclusion that it is the second order. So you will generate graphs, and that's why I say you should be well-rounded in graphing the data. I want you to download this data so that you'll have before you when you will be uh, completing the data sheet. Here is the data sheet, and I want just go step by step on how to fill in the data sheet. You need to fill in the data sheet, your name and the date. This is the suggested mass of oxyclean. And if you look at the oxyclean, it has peroxide. For every 1 mole of oxyclean, there is 1.5 moles of hydrogen peroxide. And this is the mass for this experiment. For the simulation I did to collect the data you're going to use, this was the mass of oxyclean, not the peroxide. So you need to bear in mind how you will use the mole ratio to determine the moles of peroxide, because you need what? To find the concentration of hydrogen peroxide. You know what these big parentheses stand for. This stand for concentration, which means we need to find what? The number of moles of peroxide divided by the volume of the stock solution, divided by the volume of stock solution. When we say stock solution, it means the solution you will use in subsequent steps. In part 2 and part 3, there are 3 parts. There is part 1, there is part 2, and part 3. In part 1, preparation of stock solution, we need to know the number of moles of the peroxide and the volume. You are given the total volume here. Remember to change that to moles. So with an understanding on how to find the molarity, all right, you need to determine the number of moles of peroxide over the volume in liters, which you know this is what? This will be 0.100 liters, because in 100 ml change that volume. But how are you going to find the number of moles of peroxide? You already know the mass, all right? Using the molar mass of please, and double check the exact mass of oxyclean. I think this is what it is. Let me just give you the exact one. It is 157. All right, point what? 0.1 grams. This is one right here. Grams per mole. That is the molar mass. This is 0.01. 0.01 grams. That will give you the number of moles of oxyclean times 1.5 moles of peroxide using the mole ratio. That is what we need to fill in this equation to find the concentration of the hydrogen peroxide in the stock solution. So you're gonna fill in, and please, you have to show your calculation. Not in this space, you may attach extra sheet of paper, and please label it as part 1, A, preparation of stock solution. Preparation of stock solution. That is it for part A, part 1A, part 1A. Now let's look at part 1B, determination of order of reaction with respect to uh, Plu one die. We need to find at the end of the day, you'll write the rate, all right? You'll write the rate of reaction with respect to, let's see, rate here is K times hydrogen peroxide, all right, raised to some value, and then uh, blue dye one. What is the reaction order? M and N. What is the value for M and N? So for blue dye, based on the instruction, all right, based on the instruction given, you'll have to determine the collect the data based on the rate at which the bleaching kinetics of peroxide in oxyclean decolorize the colored food. So what happened here is based on the direction given in the handout, these are the values captured by the color detector when I collected 3 times, all right? These are the values collected for the Planck 197, 199, 198. You need to find the average, all right? You know how to find the average. Okay, divided by 3, it's gonna give you the value. We call this initial. We're gonna need this value. Later on, I'm going to show you where this will come in. Please take note of the subscript O. Now here is the experiment now at different times. At different times, you these are the values collected after 60 seconds, after 90, all the way to 400 and all the way to 408, all the way to 408. Each one of them has 3 values which were consecutive. I had to take a snap of that. You will find the average color value for each one of them. I know you know how to find the average. If you are using spreadsheet or Excel, you will type that as well. Or if you are doing it manually, that's fine as well. And then here the calculated observance, all right? Observance, let me just show you that. Observance based on this equation, look at this equation. Observance is given by, uh, this is given by the A equals to negative log of what? Negative log of R, which you will be determine that this is the average. I want to say this is the average right here, average. And this is the R naught given P4. This is the R naught given P4. So you will need to understand that so that you have the value for the value for observance. This is the observance value, calculated observance. You will use that equation. R, this is the R value. R naught will be, all right, R naught will be the given, all right, R naught will be given from the equation, from this value given here to get the observance. Once you get the observant values here, you will now determine the natural log of the values you have calculated for observance. We'll abbreviate that as APS and the reciprocal for this. So I think you will have to only determine whether it is first order or uh, whether it is first order or whether it is the second order based on the graphs you expect, all right, based on the graph you expect when you plot the data. I think this is what you will do with the data, all right? This is what you will do with the data and compare with your values. These are the graphs I walked you through before, right here. If you look at all what you have to do is see if it is first order or if it is second order. So there will be two graphs you will generate. Natural log of concentration or observance, not concentration. So yours will be, all right, yours will be here, ln of natural log of observance, APS, versus time on y-axis. And then you'll also have the reciprocal of APS observance. This is ln of APS, because we know y observance from the Peirce law, A equals to concentration times what? Path length times the epsilon naught, all right? There is the epsilon naught, which we know observance is directly proportional to the concentration. That's why we are just taking observance, which is directly proportional to concentration. So if I do have, or if you end up with a straight line, see natural log of observance, and please indicate the units, end up with a negative slope, you know it is first order with respect to blue dye one. All right. If you end up with a positive slope with the reciprocal on y-axis for observance, time on x-axis, your conclusion is second order with respect to uh, blue dye one. That's how it determines graphically the rate at which blue dye is uh, reacting. That means you will get the value for n, in this equation, the value for n in this equation. You will graphically determine using this. You may not, you may notice that might not be exactly the same, like, you know, this or this. I'll go with the R value, use, all right, use or R trend line, all right, of which the closer to one, the more you make a conclusion is third order. For example, I may have trend line here where R square is 0.992, and here I may have 0.955, I mean 0.9997 and 0.952. You know, this one will be lower. I'll go with the fast one and vice versa. So please include the trend line in your plot. Include the trend line in your plot and see whether it is first order or second order. This is first, and then this is the second. That's what you will do in determining the order with respect to it, with respect to the blue dye, with respect to the blue dye. You know, what plot was the most linear? Was it first order or was it second order? You need to make that conclusion. If it is first order, you will say, you will put here one. If it is second order, you will put here two. That's what you need to remember. What I'm looking for here, it is from the graph. And please attach your graphs. That is all for part one. That is all for part one. And please take note of the composition of the solution. All right. The solution was made by mixing, all right, by mixing 80 ml of distilled water, 20 ml of stock solution, which you know the concentration of the stock solution. You prepared the stock solution and you took 20 ml of the stock solution to prepare or to use in the reaction in part 1B, and of course 1 drop of blue 1. So let's move on to the second part, all right, that is part 2, using method of initial rate to determine the order with respect to peroxide. So now we are shifting gears to this, let me just show you my whiteboard. We are shifting gears to how do we find the value for M right here? How do we find the value for M? We are using the method of initial rates, which we covered in the last or previous experiment, all right? And first, we need to find the concentration of the peroxide. We need to know the concentration of peroxide, which we know, all right, from the stock solution. Let's see what is going on in part 2. I will not read the direction, but please go back and use the handout. But here is what was done with 1 drop of dye. You read the instructions, tell you weigh and empty, all right, graduated cylinder or something like that, to determine the mass of 1 drop of dye, and it was determined to be 0.4 grams. So to calculate the concentration of the blue dye, blue 1 dye in 100 ml mixture, we know the volume of the what? Volume of the solution in ml. We know the mass of, all right, the mass of the 1 drop which was used for the reaction. And with that, to get the concentration, right, to get the concentration of blue dye here, all right, concentration of blue 1 dye, this is the number of what? Number of moles of volume in liters, which we know this is 0.100 liters. This is the volume of the reaction mixture. Now, how will we get the number of moles? Number of moles here is given by what? This is given by mass in grams of molar mass, all right, molar mass of blue 1 dye, molar mass of blue 1 dye, which is given here. This is the molar mass. Look, this is the molar mass of the blue, all right, blue 1 dye. This is the molar mass. And given the mass here, mass over molar mass give you the number of moles. You plug that in here, the concentration. Once you know the concentration, all right, you may have it xxx dot xxx, all right, and just giving you what you may have. I'm just gonna give you that as the concentration. Now, since it's the same, this will be the same. This will be xxx, all right, 3x, and then here is xxx. It's the same thing because we don't change the concentration of the blue dye in part 2. Now, remember we are now going to determine the reaction order, which means the concentration of peroxide should be changing. In part 1, please read the direction in the handout. It's talk about using different volume of the stock solution. In run 1, We're using 20 ml of stock solution. We're using 40 ml of stock solution, and we know the concentration of peroxide in the stock solution from the preparation of stock solution. You should have that by now, which means to get the concentration of peroxide in run one, let me just put right here, I'm just gonna hide this. I'm just gonna hide this and say, let's say uh, for run one here, run number one, concentration of peroxide, we'll use M1, V1 equals to M2, V2, you can use the dilution law. This is coming from part what? This is part 1A. This is from part 1A. You should have that from part 1A. How many ml did we use? This is 20 what? 20 ml. And this is what you're looking for. And this was diluted to 100 ml. This is 100 ml. Just to give you on how you will calculate the molarity of peroxide in run 1, we use 20 ml of the stock solution. Now let's see run 2. We are using what? 40 ml of stock solution. So I'm just going to walk you through again on how to find the, for run what? Run number what? Run number 2. Run number 2. So we know M1 V1 equals to what? M2 V2. M1 V1 M2 V2. This is from what? Part 1A. All right, you should know it by then. This is 40 ml. This is 40 ml because you are taking 40 of solution, stock solution. This is 40 ml of stock solution. This is now the one we are looking for. This is the one we are looking for. And the volume here was diluted to what? To 100.0 ml. It was diluted to 0 ml. You don't need to change to liter. So this is M what? M2 equals to M1 V1 over V2 over V2. That's what you will use to fill in the table for what? For the concentration of peroxide. Remember, this is the concentration. That's why we're using M1 V1 M2 V2, the dilution law, to find the concentration. Now, to get the calculated initial rate, all right, we will take this value here, whatever you'll get here, divided by the time. Remember, rate, just gonna show you on my whiteboard, rate is given by change in what? Concentration of, it was constant. This is blue 1 die of change in time. So I'll take the what? I'll take the whatever you'll get for x over the what? 300 and what? 150, I believe, or 140 right here. This is the time you will divide. Remember how we divided by time last time? Divide by time. So whatever you get here, divided by 300 will give you the rate for run 1. For run 2, the rate here, which is the same, remember this is constant, we will get or divide by 140 to give you the rate for run 2, rate for run 2. And since you know how to find the, this concentration is constant for both, we need to find the concentration or the reaction order with respect to M. So let me just give you the layout on the calculation. So if I have run one or rate two, let's say rate two over rate one is equals to K1, no, K2 over K1 times the concentration of blue dye raised to M over concentration of blue dye or blue one raised to M times concentration of peroxide, which you are looking for. I should even use a different color coding. This is what we are looking for. Or peroxide raised to N concentration. This is M, by the way. Peroxide raised to N. So that in method of initial rate, remember you hold one reagent constant. Cancel that if you're looking for. In this case, this will cancel out. This will cancel out. This will cancel out. All right, this will cancel out. We will remain with for peroxide. So in other words, what will happen here is since you know the rate to here, when you do that calculation, xx, whatever you get here, divided by 140, you'll have rate 2. xx, which is the same as this, divided by 300, you'll have rate 1. So rate 2 over rate 1, you'll give you that value. And you know now, you'll get a value. Let's say my peroxide, all right, my peroxide, when you divide the two numbers, raised to N equals to y or y, I'm just giving you some value. When you divide the two, rate 2 over rate 1, I'm assuming that you will get y there. You do the log and say N log of, when you divide the two numbers there, A, just making up some numbers, when you divide the concentration of trial 2 over trial 2, where are those numbers? The numbers you will have here, this is the concentration for run 2, concentration for run 1. You'll have actual values in there. So those actual values, when you plug in here, you'll get one value. I'm calling AA equals to log of y, which means the exponent n or reaction order for peroxide is given by log of y over log of what? A. This is what we looked at last time using algebra to find the reaction order with respect to peroxide, So at this point, you should have the reaction order with respect to each reagent. That is blue 1 dye and peroxide. Blue 1 dye and peroxide. With that, all right, so where are we going to put the values? Here, all right, this is just a calculation for calculate the reactant or order or reaction order for peroxide. Reaction order for peroxide. We have used method of, or you will use method of initial rates. Please show me that you use that method. Go back again to my whiteboard and follow the setup so that you end up with this is method of initial rate to show me how you arrive at the what? At the reaction order. Make it a whole number, all right? Don't say it is 1.38 or 0.5. If it is 0.5, that is 1. If it is 1.1, that is 1. If it is 1.2, that is 2. If it is 1.2, that is one, sorry. If it is 1.9, and then you round off to 2 and so forth. So make it our whole number. That takes care of uh, part 2. Please, you may attach extra sheet of paper if this space given here is not the is not enough. So let's move on to part 3, determination of the activation energy. All right. In chemical kinetics, activation energy is the energy required to initiate a chemical reaction. It is the energy required to initiate a chemical reaction. Some authors define activation energy as the minimum amount of energy required, or which must be surmounted by the reagent to form the product. I draw the energy profile picture on the reaction kinetics. All right, the reaction kinetics. Here is the energy on this side, and here is the time. I may have time. You'll see in some reaction profile that this is EA, which is the activation energy A plus B to form C plus D, which is the product activation energy. In this experiment, you will determine this term, the kinetic term we call activation energy. We use EA for activation energy using Arrhenius equation for 2-point. For 2-point, you use Arrhenius equation, and Arrhenius equations look like this. Arrhenius equations look like this: ln of, or we can look at the natural log of K2 over K1. This is K1 equals negative, or EA of R, which is the universal Car's constant, 1 over what? 1 over T2 minus 1 over T1. T2, 1 over T1. It is given in the handout how to use the, or how the equation look like. Let me just make sure that give you the right equation. I think there is a negative in form. This is the Arrhenius equation you will use to find this term right here. Remember, there is the negative sign. I may just plug the negative sign to go with R, all right? And remember, me use my whiteboard. R is the universal class constant, and most students do make mistake of using 0 point, all right? 0.821, but this is the universal class constant use wherever you are calculating the energy, 8.314 joules per mole. So remember this, and the value will catch will be in joules, This is the rate constant for temperature 2. This is the rate constant for temperature 1. Of course, temperature has to be in Kelvin. This is in Kelvin, or temperature in Kelvin, change to absolute value, I will just, I'll just have the negative go with R, all right? I'll just have this go with R, so that if I want to find the activation energy now, you have to manipulate the equation so that you have natural log of K2 over K1, all right? Over what? Negative R, all right? No, times R here, times negative R. Rearranging that equation of here 1 over T2 minus 1 over T1. This is the equation. What I've done here is to rearrange this equation here to, rearrange that equation to make the activation energy the subject of the formula. What I did is the negative you see here for EA, I'm just moving around with the R, I'm attaching the R here. That's where I have negative R here. And remember the value for negative R is 8.314 joules per mole per Kelvin. Temperature has to be in Kelvin. So this guys here has to be in Kelvin. And we know rate constant 1, rate constant 2, natural log of the value, get that, negative, you will get the activation energy in joules. All right, in joules you can change to kilojoules if you want. All right, if you want. Let's see, let's go back to the handout. And in activation energy, in determination of the activation energy, we will run, or I ran the experiment as in part 1. It was at room temperature, which is around 19 or 20, see that? And then at an elevated temperature based on the handout, please read the instruction for part 3. And in the reaction mixture for this, I had warm water at 80 or around 50 degrees, and this is the amount of distilled water, and 20 ml of stock solution, still the same stock solution from part 1, and what? 1 drop of blue dye. So what you will do is find the average. These are the color captured by the app on my phone. Snap 3 times, and this you will have to find the average red color value here, red color value here, red color value here. You will calculate the observance. Remember the equation for observance? The equation for observance, A is determined by, all right, maybe even abbreviate this as observance. APS equals to negative log of negative log of what? Negative log of R, which is from the experiment average, all right, over R naught. R naught is from experiment 1, right? Look at part what? Part 1. This R is from the experiment. This is the average. This is the average. From here, all right, from here, average will be your average R value. This is from part 1, all right? This is from part 1 here. And that will give you the calculated observance. Here I'm abbreviating it as APS. It's the same thing, all right? It's the same thing. Now, how are you going to do, or what are you going to do with this? Based on what tested positive in part 2, all right? Based on what you will determine if in part, all right, in part 2 or part P, on P, if this tested positive, you will plot this data again if it stated positive for 0 order. If it is first order, that means you will plot this data, all right, as natural log of observance values. Don't give me concentration, it is the observance values. You may say ln of APS for observance, or you may say concentration of observance. Please have the title of your graph. It is a plot of observance versus time, and on x-axis indicate time in what? Is it days, in its minutes, or is it seconds? So you should have that. So the point here is once you connect the data here, you will plot this data. If it is in the previous part, you determine the reaction order to be first order, you will plot this using first order procedure. If it is second order, you will plot this using the second order and include the equation of the straight line, all right, with the R value in your graph. So with this, let me say if I have, for example, I'm just making up this. Do not think that this is going to be the case. I don't know what's going to be. Let's say I put one of our observance right here, APS, like that, for second order, all right? And then I end up with the what? With positive slope. So K is equals to slope. Remember, slope is obtained from y equals to mx plus b, mx plus b, which is this right here. This is the slope right here. This is the slope, and this is the rate constant. All right, rate constant. From the slope of the line, it is the rate constant. It's given here. Look, rate constant K. Rate constant K is given by, the slope of the line. Slope of the line. How are you going to get the slope of the line? Equation of the straight line where M is the slope and B is the y-intercept, of course. So if in part one, I had 1 over b as positive, and then this part also will be 1 over the observant value. If this was positive, if natural log of observance AP as on y-axis in part 1 tested positive like that, all right, this natural over time here, and then I'm just gonna have that slope, and please make it positive. This negative here is to make it positive, so I'm gonna have it as k equals to k. You'll never have a positive negative slope like that. Give you the value for k. Give you the value for k. So the negative here to make it positive. I don't want to see negative values. Just make it positive. This negative is to make the value positive. Negative and negative make it positive. We don't have positive negative here because already the slope is positive. So that's what you need to remember, that you need also to add equation of a straight line, all right, and add trend line, that's the R value, all right, based on what tested positive for that, based on what tested positive for that. So I'm just going to show you how to, all right, show you how you will use that to determine the activation energy. Find the average, calculate the observant values, and this is the summary of the table you will use to calculate the observance values. I'm just going to show you that. Well, if you look at the concentration, this is the same concentration from the previous chemical composition for the reaction mixture. You know the reaction for blue dye is the same as the one you used before. Same for blue dye, you'll do the concentration of peroxide, all right? For from part one, what was the concentration of blue dye? From part one, what was the concentration of hydrogen peroxide? These were the what? These were the temperatures. Find the average. You'll find the average for the temperature here. Okay. Change that to Kelvin. You will change that to Kelvin. You know you have to change to Kelvin, adding 273. Adding 273, and then find the reciprocal of that. Why are we doing the reciprocal? Because we're going to apply in the Arrhenius equation. Remember Arrhenius equation? Arrhenius equation My whiteboard here is messing me a little bit. Let me just stop this. I will exit and then come back again. All right. This is, I'm going to try and pull up again my whiteboard. All right. If hopefully this will work. This works. All right. This is my whiteboard. And what I was saying about the value for activation energy, you need to plot a graph. So here is the information you will need for activation energy. Come back here, we're gonna go through the summary on how do you find the activation energy. So once you have that, there will be, all right, part 3 here. This is what I want you to read. For each of the temperature troughs, that is room temperature and elevator temperature, you'll prepare a straight line plot, which you already determine in the room temperature. There are two values for K. In this case, there is the K, there is this value K, and then there is the K, the prime there. Take a note of that. All right, the K and the K prime, they are not the same. We call this pseudo rate constant. This is called rate. We call this rate constant. And then this is pseudo rate constant, pseudo rate constant. This is S constant. How do you manipulate that, or what is the relationship between the two? Here, these are the values from the plot. So if you have two graphs, room temperature and elevated temperature, what is the slope of that line? And remember, it got to be positive. These are the slope. These are the slopes of the straight line for part 1 and part 3. The numerical value just of the graph, you're just gonna plot in here. How will you end up with a pseudo rate constant with the apostrophe here? Since you already know, look at the equation here. Since you already know the rate constant from the slope, you know the concentration of, all right, you know the concentration of peroxide for run 1 and concentration of peroxide for run 2, trial 2, you'll plot in the reaction order with respect to that to get the pseudo. So what I'll do for pseudo is K is given by the what? The rate constant from the slope over the concentration of peroxide, all right, to there raised to N, which is the reaction order with respect to peroxide. So that's what I'll do to find the pseudo. And then calculated rate constant, calculated rate constant is given by K. This is calculated. K is given by the pseudo. Here is the pseudo. Pseudo over, all right, over the concentration of peroxide raised to N, concentration of peroxide raised to N. That is to get the calculated what? Calculated rate constant. So you're gonna do K1 at room temperature. and K2 elevated what elevated temperature, which is K2. With these two values, we should have rate constant 2, all right? We should have rate constant 2, rate constant 1 and 2, which you will plug in this equation. From here, of course, you know temperature average for temperature 2, average for temperature 1. You already have the reciprocal of these values. You rearrange to get the activation or energy. You rearrange to get the activation energy. From there, you should be able to write the rate law, write the rate law using the rate constant from the room temperature trough, from the room temperature trough. Please, as always, you should show all your calculation, show all your calculation. If you have any question, please do email me. If times allows, I will schedule a Zoom meeting for further assistance. Other than that, that's all what I have for you as far as experiment on monitoring the kinetics of bleaching using smartphone. Thank you and good luck.